that is fixed. Let's imagine that there is no latent period, there is no delays, etc., etc. The only things, and we also imagine something also that is very strong. So we imagine that this is a very acute disease that we are describing on a time scale, for instance, 1 day, and we do not discriminate what happens within the day, so the fact that there are different perhaps stages, etc. And so we imagine that the infection is immediate. As soon as you get infected, you start to be infectious the next time step for the other individuals. And there are no hospitals, no medicines, no behavioral change of people. So we disregard all the things that actually are interesting, but we want to do a very simple thing that is describe susceptible, infectious, and recovery individuals at the end of the disease. Those basically monitoring what is the number of susceptible individuals in the population, the number of infectious individuals, the number of recovery individuals as a function of time. What I'm assuming is that the sum of individuals in each of these compartments, in each of these boxes, or if you want, with the label S, I, or R attached to it, is constant. So the sum will be the sum, and then we forget about it, all these other attributes. And so that is the first step, okay, of a model. So we have a conceptualization of the system. Now, this is equivalent to when we were saying yesterday, the past class about the models of Granovetter, etc. So this is the descriptive model. We have defined that in the population there are the susceptible individuals, the infectious individuals, and the recovered individuals which are immune to the disease. It's an hypothesis that is a little bit easier to validate than the weak or strong ties, because from clinical study, from the doctor on the field, that the individual is susceptible, is infectious, and after you recover from the disease, you cannot get the disease again. However, it's still just completely conceptual, is descriptive. Of course, there will be a flow of people from this compartment to this compartment, and from this compartment to this compartment, and I will have a dynamics at this point that I'm not describing yet, in which if I have an infectious individual in a fully susceptible population, I will start to generate other susceptible individuals, some of them will recover, and so on and so forth. This is what I expect. The epidemic will progress in the population and will generate cases and will generate people who are immune to the disease and so on and so forth. Now, this qualitative model is one thing. Now, what we want to do is to find those question marks and write an explicit dynamic for the model. Okay? So, where do we start? Ta-da. Now, this is even more end of the world scenario. Because, wow, this is bad.
Maybe we need something other than a star to clean the board.
We need something better, than this for cleaning the whiteboard. Although
maybe it's just that marker.
These markers are tougher too.
Yeah. This one came up.
Now you have to ask me the right question if we want to go into this modeling exercise. Okay? Because you cannot know everything, and I will have to give you some information. But the first thing is that, again, keep in mind what we did the other time. Mm-hmm. What is the first things that you... So now what we want, what we would like to know?
We would want to know the conditions under which someone goes from susceptible to infected and from infected to recovered.
And this is the microscopic dynamic. So This is one piece.
One person.
So one piece is microscopic dynamics. So let's start writing that. Because this is We don't write the microscopic dynamics. This is one of the elements we need.
So,
No? Yeah. This is so. Let's first find the pieces we need. One is the microscopic dynamics, and then what do you want to do with the model? So how you provide a mathematical description of this?
So that's basically just the number of susceptible, number of infected, number of recovered at each time step.
Good. And
so it's three separate. Well,
perfect.
Yep.
Good. So what we need to do now is to write ST, IT,
and RT.
RT, and what we did the previous time. What we did with the random walk is that we were relating the value of this variable at time t plus 1 with the value of the variable at times t.
Mm-hmm.
So this is what we need to do, okay? So we have those three.
So would it be lowercase t? Would this be the first part at least? Since
No, because we need first the microscopic dynamics. So
well,
here,
okay, so wait, so we're starting at the micro. Okay. So
because we need to know when an infectious individual will turn in.
so we're just focusing on. We're not just doing the. Okay.
Yeah.
Okay.
So now so you have a vector is ST, IT, RT.
Mm-hmm.
And then for each of these, you have to imagine that each of these compartment is like a box in which you have individuals.
Yes.
And now you move individuals from one box to the other.
Yes.
This is what that counter ST will tell you. But now you don't know the function that moves those individuals around.
Yes. So
This is where you cannot
so
just
wouldn't it totally
yeah.
depend on the whatever virus we're talking
whatever
about?
disease and whatever.
Network.
So we need, first of all, to find the process that brings one individual into the recovered class.
So everything that we're talking about so far that's just a function of the time it takes to recover.
Good. What is the times that takes to recover?
It's sensitive to whatever the disease is.
Yeah.
Right?
Good. Perfect. So the first things that you have to do to construct this model is to go to a doctor and ask, okay, if you have somebody who gets sick into your hospital, how many days it takes to recover?
Mm-hmm.
And this is data that you can access clinically, or you can try to measure. It's not always available.
Mm-hmm.
And let's imagine that I tell you that the time it takes to go from one infectious to a recovered, from the infectious state to the recovered state, on average, is 3 days.
Mm-hmm.
How we would describe then the transition from I to R? It's on average. So that means that some individuals will probably take 1 day, some individuals 2, some individuals 3, some individuals 4 or 5.
Mm-hmm. Okay, so if we have a set of individuals that are infected,
Mm-hmm.
Wouldn't we just end up calling it, well...
So, yeah, I guess it depends on
It depends on
what our
like,
assumptions are in terms of like.
Because if a whole bunch of people get infected on one day and then not as many for the next day because of some reason,
Yeah.
then it skews it, right? So that, but I assume we're not thinking of those types of cases. We're simplifying.
But
For
this
one
is
individual.
This is the good thing. What you need now here? What is that you need here? If you have an individual that has in R, what you have to put in that? Remember what were we doing with the with the random walk. What was doing the random walk? We need a probability to move from one node to the other.
Mm-hmm.
So
So
here
the probability.
we need a probability to go from I to R.
So the
And
probability
it's
would just
3
be
days average, so it's a Poisson distribution.
Good.
Yeah.
And if it's a Poisson distribution with a 3-day average, I can tell you something that I will leave you to show for the next time, that the probability is the inverse of the time.
Yeah.
so just
It's
1/3.
1 over
Yeah.
Is it just 1/3?
1/3.
1 over lambda. Yeah.
Why?
Okay.
Because in a sense, if you do the expectation value
The
of probability times time, you will get a unitary value after 3 days. And so this on average, it tells you that this is the thing. So,
Okay.
so basically the probability to go from here to here is
On average, a
1/3.
Okay.
So let's start giving a name to those variables. And so we say that this variable that is the recovery probability is equal to mu, okay, or any other symbol you want, and is equal to 1/3. Let's write down.
So we'd say
We do this, well, we do a simple thing that is to consider. You say, this is I, this is R,
Mhm.
and this happens with a rate or a probability which is equal to 1/3.
Mhm.
And actually, I don't, at this point, when you have these things, you don't care even anymore if it's 1/3, 1/4, etc. Okay,
it's
the doctor will tell me what is that.
Mhm.
Okay? Now, let's suppose that I have, now, if I have one individual,
Mhm.
or I have 100 individuals in this compartment, what will be the number of transition per unit time?
if you have 100 of them.
On
That'd be
average, 33.
Yeah, that'd be
So,
be multiplied
let's
by
imagine
30.
that this is IT. How many will do the transition at that point?
So how many? So we know how many individuals are infected at time t,
Mhm.
and how many recovered are we going to have at t plus 1?
Yeah,
It's going to be however many
Is
are
it-
recovered at time t plus mu times it.
good.
But there's going
Perfect.
to be some
So,
variability.
now, and this is again the usual trick that we do in the modeling when you have dynamic modeling. We say, okay, this is IT plus 1. IT plus 1 will be equal to IT, and then we call it minus, IT
Mhm.
minus IT
IT
minus, so the one that goes out of the compartment, plus IT plus, which are
Which
the
are the
one
new
that comes,
infections.
the new infections.
Yep.
So what we are calculating now
Is
is
I-
this
is
I
IT
minus.
minus. Yeah.
And what we say that is IT minus is equal to mu
Times
times
IT.
IT on average.
Yep.
Okay, so that's
Yeah.
that's pretty easy enough. Well, let's reason on this, because now there is a very, very important thing that we are assuming here. If I have 10, 100, 1000 of this IT, this probability doesn't change. What does it mean, this? This is probabilistically means that you have an independent process. Each
Mhm.
process of recovery is independent on any other process.
Yes.
Why we are doing that? Because in a disease we assume that you are infected. It's just your immune system at that point that decides if you recover or not and when you will recover. So it's totally, if the both of you are sick, if he recovers or not, your immune system
Doesn't care.
doesn't care. And so, this
That's
is an
reasonable.
independent process.
Yeah.
Keep in mind, this is exactly what is not happening in social contagion.
Mhm.
If you change your mind, if you become immune to an idea, etc., and you're a friend of somebody, your recovery will influence the other people.
And you can prolong.
And so this is completely different. That would be a different way of writing this term.
Mm-hmm.
Okay? So this is the simple term. This is we call, in some cases, the one-body interaction, in the sense that it's not an interaction at all, because this is just himself that decides spontaneously to go from one state to another.
Mm-hmm.
Okay? And this is always like that. Now, if we go back to this, let's imagine that we have a model that also considers people in the incubation period. The people that goes from the incubation period to the symptomatic period
Mm-hmm.
will have the same kind of one-body interaction.
Mm-hmm.
Because that just depends again on your immune system, on your way of manipulating information, if you want, at the biological level.
This is just considering how long it goes into.
And so you will need to know from the doctor what is the average time of the incubation period. Then you do the inverse, you get a probability, and then you get into the clinical disease stage. And all those kind of what we call spontaneous one-body transitions are always like that. I will be nasty at a certain point, and I will show you that we need to do some variation. Here, what he was saying was very important. This is true for a Poissonian process. So you assume that there is a more than is Poissonian, or if you want, is a binomial process, and that's the other important things we will see today. In some cases, it might not be like that. For instance, the distribution could be skewed. A lot of individuals recover after 1 or 2 days, but then the distribution has, cases that takes a long time to recover. And that will change that things, because it's not, mu is not anymore equal to 1/3. Then you need to have a different way of modeling the stochastic process. Now, okay.
Do you have Poisson? It's just a.
Yeah.
Okay. Yeah.
It's more or less a normal distribution.
Yep.
Yeah.
Just with.
Is a normal distribution.
discrete
Actually,
variables.
is the continuum approximation of the binomial distribution.
Mm-hmm.
The Poissonian is when you have a binomial. Binomial distribution is when you have a probability of success for a certain number of events, and then you calculate what is the probability of 1, 2, 3, etc., successes.
Mm-hmm.
If you have an infinite number of trials and a very tiny probability of success, because otherwise things do not work, you get a Poissonian distribution. That at that point doesn't need anymore the number of trials.
Mm-hmm.
Here we have the number of trials, because we have a certain finite number of infectious individuals. We need to keep in mind that most of what we will do, we always work with individuals. That's all the class in the next 3 months, 4 months. And so we need to keep alive this integer representation. So we're talking about discrete quantities. And
Mm-hmm.
there are a lot of issues by going into the continuum approximation, just because we are creating 1.5 individuals, and that's not fully correct, as you can imagine. Okay, so this is the simple part. Okay, you have a time of recovery, you define a probability that is the inverse of the time of the recovery, and then you have a variation that actually would be negative in this case, mu times I. Okay?
Mm-hmm.
Here, in some cases, you will find that there is also time explicitly represented, because you might say, okay, I have a probability per unit time, so I could change my time scale, but generally the delta t, the time that you consider, is 1. And that 1 could be 1 second, 1 day, 1 month, depending on rescaling all the other numbers. Okay, this is the generalization. So all spontaneous transitions are like that. Now the problem is here. Because now the susceptible to infection, that is not depending on yourself.
No.
That is depending on your interaction with the other people. And so, what would be a way to model that? Well, let's start from this piece of information.
Mhm.
No? So, obviously, if we are in Boston and there is one infectious individual, your probability to be infected is much smaller than if we are in Boston and there is 200,000 infectious individuals, no? Because
There's more contacts.
there is more contact, there is more possibility during the day to get infectious, no? To get in contact with an infectious individual. Now, what you have to, again, picture in your mind is that your number of contacts more or less is the same. What you have here is that if there are a lot more infectious, you have a larger probability that those contacts will be with infectious individual.
Mm-hmm.
And so how you would model, now what we need to get is what?
The number of
You were, yeah, look, yes.
number
Okay,
of
the
infections.
plus. And so what we need a probability, no? That a susceptible individual will turn into infectious. And how you would guess this probability?
So it would be, I mean, it's simply,
It's going to rely on the
It's-
number of
not the number, the proportion, right?
Good.
yes, the number
Proportion of-
proportion of
Contacts that have the disease multiplied by some other factor that represents,
the infection
the-
rate.
yeah, well, like the potential that this disease has to infect people. or
Perfect.
something.
And so how you would write that mathematically?
Wouldn't it just be something like? Are we at the?
So it's IT.
Can we talk about the node level? Or we're still talking about the system
Let's
level?
talk about one. So what is the probability that one susceptible individual will be?
For one susceptible.
Mm-hmm.
So we just say like for node I.
Yeah, let's do
Okay.
for the node I.
So it'd just be
Portion of their contacts
yes, it'd be.
that are infected.
Do we want to say like the neighbor? So you could do something like this.
I mean, this is what the class is going to be about. So it's homogeneous mixing in all these early models, which is just assuming that everybody's like, I don't know if that's where
Yeah.
he wants to go with this.
This is,
yeah. That's like
you
the
have to
simplest
tell
way.
me, you want to start from something more complicated, we could start from something more complicated, but then
Yeah.
you will need more information, no?
Yeah, yeah.
So let's
this is
imagine we
more
don't have that
complicated.
information.
This
Let's
is
what do
how
you
the
write?
adjacency matrix.
Yeah.
Oh yeah, you need the adjacency matrix here. We will get there. But now I tell you that we don't have it.
Okay. So we don't.
I need something simpler because we don't have that information. So that was a good start.
Okay.
But we don't have it. So
Okay.
what you would do to do something simpler than that?
So we just assume everybody's mixing all the same, which is a little ridiculous, but that's what we're going to do.
Okay. Okay. So then.
Yeah, but look at, put yourself in the shoes of, it's you in Boston, and what is the probability that you get infected?
Would be the number of susceptible individuals at time t minus.
No, you are susceptible.
I am susceptible. We're still talking
About
about
you, I'm talking about you. What is your probability per capita? Then we will do all the numbers for that. But now, you are one susceptible individuals in this pool of people.
Can we just say that it's the number of infected people over the rest of the population?
That's a good start. That means that you have, your probability is proportional
Proportional
To
to the
the-
number of infected
yeah, how you would write that? We know that the total number of individuals is n.
Yeah.
So that means that probability.
So you'd say IT.
No, don't write yet IT. Now I'm interested on something else. Well, let me give you a little bit of formality in this. This is okay. Now, what you want to do is this, IT plus.
Yeah.
This will be...
Yeah, that's what we got this.
Yeah, this will be... Oh, yeah.
We're writing the other side.
Yeah, this will be equal to what we call the PS to I
Probability
times
of T over
the S of T. All the susceptible. This is the probability for a susceptible to become infected.
Yep.
Mm-hmm.
I multiply the for all the susceptible
Because
that are
that's
assigned
each
T.
a chance.
It will give me the number of susceptible that will flow in the infectious compartment.
But then we need to define.
We need to
probability
define
S of I.
this.
Yeah.
And this is what I want to know from you. So now,
Yeah.
if I'm not wrong, what you say is that PS of I
would be
proportional to I
T minus 1,
good.
right? Over N. Or
Perfect.
No,
Yeah. Good.
Yeah.
Good.
Good.
You were good. Actually, let's imagine that now it's not -1 or because we are not
Sure.
yet doing it. It's IT over N.
Mhm.
This is proportional. What else is affecting this?
The number of people that are recovering in this time step?
No. Now
The-
it's just you alone again. It's not, you are considering here, you are already considering something that is complicated in a sense. So you are making a big statement. What you have done with this expression, then I will say you as a name, and there are probably 2 or 3 libraries about it with thousands of volumes, and they will tell you. So you have done something that is very intuitive, but it's a key milestone in the scientific modeling process.
Okay.
This is, but we miss a piece here. What is that? Because this is just the fraction of people who are sick.
Yes.
So
What else you need to add?
I mean, it depends.
Let's imagine that. Well,
imagine
I am a 50 years old guy.
Mhm.
Let's even do more extreme.
Are we
I'm
just
a-
talking? I think I know where you're going.
The
Maybe
infection rate?
the degree to which this virus actually transmits.
This is one thing.
Yeah.
Good is the probability that the virus transmits during each contact.
Mhm.
And then what you need more. If I'm a 70 years old, how many people I will see during the day?
Not as many as if you are
As you.
25
Yeah.
or 27.
So what
or
we
whatever.
miss here?
Would that be
The number of contacts.
Just the number of contacts for
Yeah.
the individual, or
Yeah. So basically, what you are doing is to say,
or
if
degree?
I,
Okay.
yeah, if I have a number
Yes.
of contact K,
Yes.
on each of these contacts I have a probability lambda to get infected. But then I need to see how many of them, what is the probability that on any of these contacts there is an infection.
Yep.
Okay? So, and these 3 things will be my average probability of being infected.
Mhm.
Okay? And now, what I need to do is just to substitute this here, and so I will have lambda K S T I T over N. This is the number of
Mhm.
new infections that you had.
And we're just modulating.
Yeah.
lambda and K.
Now, generally, since we don't know this K,
Mhm.
if you are in a network, this is the information that was missing before. If we are in adjacency matrix, it's totally different, and we will have to work with that. But now, if we are not in an adjacency matrix condition, and we just know average things,
Mhm.
what we do is that we say that this number is the same for everybody on average, and is something that we are not able to disentangle. It's a rate beta, and
Mhm.
so we call it beta. So we sum up those 2 numbers in one variable because we are not able to
Define it
disentangle.
any further.
Yeah.
Yep.
Now, what is crucial here, however, is this piece here. This piece is called the mass action law.
Okay.
That is telling you that each of these susceptible individuals is exposed to something that is called force of infection. That is this probability here that each individual per capita feel, that is proportional to the mass of infectious individual in the population. These things in an individual, in a society, seems a little bit unrealistic. So immediately you see that you are doing a big approximation. We are mixing, and that was he was mentioning, homogeneously all the individuals in Boston in a single box, and we shake them. But it's not like that.
Sure.
Perhaps, there is a much more infectious people in Belmont, and since you are living in the south end, you will never be in contact with them. And so these heterogeneities, however, I don't know how to handle. I don't have enough data.
So we just drop it.
We forget, and we use the mass action law. Why the mass action law is important? Because the mass action law is what we have also in chemistry, in physics, in engineering. Every place, for example, all the chemistry that you know is based on that. There, in that environment, the things works because you have always the Avogadro number of particles, and they are always subject to Brownian motion. So they are all over the places, they are completely mixed, etc., etc.
Sure.
But to a certain point, because then, for instance, I could have a solution that is not well mixed, then I have interface effect and all those things, etc., etc. And this is where, again, chemistry and social sciences meet again. So when you yesterday talk about the Schelling model, that actually is a surface tension model in which you have a chemical reaction that occurs just at the surface, and then inside there is another nucleus, and things that we will see. But so this is your second piece. Okay?
Yep.
So now you can write the full equation at this point.
Yes.
Because you have the I minus.
Yep, and we have the...
And then you have also the I plus.
Yep.
And everything can be written. So you have now a nice equation that is I t plus 1 equal to I t minus, and then the mu I t plus beta S T I T divided n. And now, this one that seems a very simple equation, it's very elegant. The moment that you write, you realize that you are in trouble, that your life is going to be miserable. Why? Can you see that? You need to get this I right away when you do modeling.
There's an IT in all terms.
ST is equal to n minus RT minus IT. Multiplied IT. That's a nonlinear equation.
Yeah.
The probability that you find an exact solution to that equation is close to 0. And so this simple model that we have in one morning we wrote down doesn't have an explicit solution. After 250 years, actually it's impossible, there is no explicit solution. So what we can do now is to do a lot of numeric works and approximations on the equation itself in specific regime of the model that give us an understanding of the phenomenon. So we will see a lot. This is just, we are scratching the surface of this because now what we will see the next time is these values. What are now? All this stuff. What is that? This is not the number of individuals in each compartment, but is the average number of individuals in each compartment. So we are doing an average description.
Mm-hmm.
Is the average description correct or not?
No.
No.
Depends on
No.
the situation,
Yeah.
I guess.
Yeah, exactly. And we need to find a way to do a little better than that.
Mm-hmm.
20 years ago, your colleagues would stop here, in the sense that we would write this and then we would go now one way, that is differential equations, solution of the iterative equation of this, and we will do a little bit of that. But now instead, since you are 21st century guys and you know how to program, we do something different. Now from this we say, okay, no, this is not true. This is just
We actually played
the mean evolution of the system.
Mm-hmm.
So how can we transform these ideas into something that is more realistic? And here, since this is an average value, right away you will be in the situation in which you have 22.33 individuals. And the 33 individuals, you don't like that. You want to keep a formulation of the problem in which you will have 22, 21, or 23 individuals, but not, if you have 1 million individuals, the fact that you have 1 million's 0.22 doesn't do a big difference.
Mm-hmm.
And so when you have very large epidemics with a large number of infectious individuals, this description is reasonable. The
Mm-hmm.
problem is that an epidemic always starts with 1, 2, 3 infected individuals. And in that regime, that equation is not really the best you can think of, okay? Although we will learn a lot from it. But so this is the equation we start with. Now, if we have written this equation, we can also write the other two equations for the susceptible and the recovered, no?
Mm-hmm.
Can you try to do? Because what we have modeled both processes, not the susceptible that become infected and the infectious that become recovered. So now the susceptible is what? St plus 1.
Is the number that were susceptible at time t
Yeah.
minus
the
Good.
movers,
which is this.
to
Yeah.
this it
Good.
plus.
Good.
Which is
Just the beta
this
ST
guy. Yeah.
IT over n.
Substitute.
And then the RT.
The RT plus 1 would be RT plus the second term, right? Yeah.
Yep, the number of lost.
Which is just mu t.
Yep.
Mu IT.
Oh, yeah. Okay, so just,
IT minus, yeah.
Yeah.
That is
Because if we're
equal to
modeling
mu. Yeah.
if we're modeling outgoing
Yeah.
and incoming, then
yeah.
it just
So you see that now you have a nice set of 3 equations in which at each time you can map in what is the other. So to solve this equation, what you need now?
Put them in a matrix.
play it out.
Linear algebra.
Play it out. No, you cannot solve
Oh yeah.
analytically.
Yeah. Okay.
You would try for a few years, but then you realize that you cannot do that, and so you plug in the computer. To play that in the computer, you need 2 things. One is the initial condition.
Mhm.
The
The underlying topography.
T equals 0.
Yep.
Now the initial vector I0, S0, H0 are 0.
Yep.
The topography here we don't consider anything yet. Okay, so
Okay.
there is no, we keep the homogeneous assumption. And then you need the value of the parameters.
Mhm.
Yep.
Okay.
Mu, lambda.
So what is beta and what is So, since you don't know, I will tell you what is a good value for those parameters. And we will discuss that at length, but if you have mu equal 0.3,
Mm-hmm.
and then you have beta equal 0.5, and then you consider n equal 1,000, so a population of 1,000 individuals, you start with I0 equal, let's say, 10, okay, 1%. That means that S0 is equal to n minus 10, and R0 is equal to 0. Okay?
Yep.
Iterate the equations, okay? Write a simple code in which you just numerically start from those conditions and play out those equations, and then look in time to the behavior of those quantities. Okay? That's it for the next time.
That's all you want?
That's all I want.
Okay.
So
You
it
don't
will
want to
be
go harder on us?
very simple. Then if you're very good, you will start to have a look at what happens when you change the parameters, the beta and the mu.
Yep.
Okay?
So you want us to have a nice weekend?
I want you to have a nice weekend. Yeah.
It's very nice.